We continue now with the section 4.2 notes. Let's look now at some basic properties of logarithms. Logarithms have quite a few properties related to them, and we'll see some more of these as we continue through the chapter. The first one is log base a of 1 is equal to 0 for any base a. Log base a of 1 is always equal to 0. If we write this in exponential form, all this is really telling us is that if we take a and raise it to the 0 power, we get 1. A to the 0 equals 1. So the exponent a should be raised to give us 1 should be 0. The next property, log base a of a equals 1. The exponential form of this would be a to the first equals a. A to the first equals a for any base a. The next property, log base a of a to the x equals x for all real numbers x. This is a very important property that we'll use quite frequently. This is basically just, it's a very obvious statement when you write it in exponential form. The exponential form is a to the x equals a to the x. If we want to know what exponent we should raise a to give us a to the x, obviously that exponent would have to be x. And then the fourth property, a to the log base a of x equals x for all positive real numbers x, for x greater than 0. So this is basically saying if we raise a to the exponent that we should raise it to get x, that's what we'll get. We'll get x. So this is sort of turning around what's written in the third property. I'm trying to decide if I want to say anything further about this right now. Let me just try to say one more thing about this. If I write y equals log base a of x, the exponential form of that is a to the y equals x. Now if I replace the y in the exponent with log base a of x, it gives us that fourth property there. If you take a look at that, a to the log base a of x equals x, we're replacing the y with log base a of x. So this is a consequence, this fourth property is a consequence of the equivalence between the logarithmic form of an expression and the exponential form. Example 4 says evaluate the logarithms of example 3 using the third property stated above. So in example 3, the first logarithm we evaluated was log base 5 of 25. If we use this third property, we recognize that 25 is a power of 5. Log base 5 of 5 to the second. Then the third property says log base a of a to the x equals x for all real numbers x. So this would simplify just to 2. So if the base of the expression inside the logarithm is the same as the base of the logarithm, then essentially there's a cancellation that occurs. So we might call this a cancellation law for logarithms. The second example we looked at in example 3 was log base 2 of 1/2. If we recognize that 1/2 is itself a power of 2, it's 2 to the negative 1 power, then the logarithm cancels the 2 and we're just left with what's in the exponent. So this third property can be useful for evaluating logarithms if the expression within the logarithm can be expressed in terms of the same base as the logarithm. So I want to definitely draw your attention to that third property, and also the first property as well is very commonly encountered in working with logarithms, to remember that the logarithm of 1 for any base is always equal to 0. Now, thus far we've emphasized the relationship between a logarithmic expression and an exponent, but in fact logarithms can define functions. The equation y equals log base a of x defines y as a function of x. For a given base a, for a particular x that we can substitute into the logarithm, we'll get one and only one y value for that x. Basically, we're saying there's one and only one exponent that a can be raised to give us x, assuming x is an allowable value that we can substitute into the logarithm. The function f of x equals log base a of x is called the logarithmic function with base a. The domain of f is 0 to infinity, that is x greater than 0. So logarithmic functions are not defined for all real numbers. They're only defined for the positive real numbers. Let's look at an example of a logarithmic function. Log base 10, f of x equals log base 10 of x. So this is also referred to as a common logarithm, base 10. Suppose we want to evaluate f of 10,000. Then this would be equivalent to evaluating log base 10 of 10,000. Well, 10,000 is a power of 10. It's 10 to the third power. And by our cancellation property, property 3 listed above, the value of log base 10 of 10 to the third is just what's in the exponent, 3. So the value of the function at 10,000 would be 3. What about f of 0.1? This would be interpreted as log base 10 of 0.1. Now 0.1 is a power of 10. It's 10 to the negative 1 power. 10 to the negative 1 is 1/10, and 1/10 is the same as 0.1. By our cancellation property, that should simplify just to the exponent, negative 1. So for a given value in the domain of our function, we should be able to find a particular value, one value that represents the function value. And we just have the restriction that the value we substitute into the function must be a positive real number. Since logarithmic functions are functions, we should be able to graph them. And the method for graphing a logarithmic function might be to replace f of x with y and then convert the logarithmic equation into a more familiar looking exponential form. Let's demonstrate that with the graph of f of x equals log base 2 of x. If we replace f of x with y and write y equals log base 2 of x, let's rewrite that as log base 2 of x equals y, just switching the two sides around. If we convert this to exponential form, it would be 2 to the y equals x. 2 to the y equals x. So in filling out a table of values for this logarithmic function, we're essentially working with an equation of the form x equals 2 to the y. So it would be reasonable here, because of the form of this equation, to actually first choose the y and then solve for x. So that's what I've done in the right-hand column of our table of x's and y's. I've selected some y's, negative 3, negative 2, negative 1, 0, 1, 2, and 3. These are going to be exponents that 2 will be raised to give us x. So to compute the x value for y equal to negative 3, it would be 2 to the negative 3 power. That would be 1/8. For y equal to negative 2, the x would be 2 to the negative 2. That would be 1/4. For negative 1, it would be 2 to the negative 1. That would be x equals 1/2. For 0, it would be 2 to the 0. That would be x equals 1. For y equal to 1, 2 to the first is 2. For y equals 2, 2 to the second is 4. For y equals 3, 2 to the third is equal to 8. Now, this may kind of look familiar to you from when we graphed y equals 2 to the x. The only difference is that the roles of x and y have been interchanged. Previously, for the exponential function, we selected x's and solved for y. We selected the same x's that we're using as y's in this example. So now the roles of x and y have been reversed, and we're essentially working with the same values, but with the values of x and y interchanged. Let's plot these points now. 1/8 negative 3 would be very close to the y-axis, so I'll put that about right here. 1/4 negative 2 is about here. 1/2 negative 1 is about here. 1, 0 is an x-intercept. 2, 1 would be about here. 4, 2 here. And 8, 3 here. So now I've connected those points with a smooth curve, and you can see that's the basic shape of the graph of a logarithmic function. You see it's passing through the x-axis at x equal to 1. It goes along the y-axis asymptotically, so the y-axis is acting as a vertical asymptote, and then as x's increase, the function values increase, but at a slower and slower rate. So the graph gets flatter and flatter as x increases, although it never becomes horizontal. It's always increasing, at least for this particular logarithmic function. Having viewed the graph of a typical logarithmic function, we can now state properties of logarithmic functions in more generality and contrast those with those of an exponential function that we listed in section 4.1. So for a logarithmic function, the domain is 0 to infinity, the positive real numbers, and the range is minus infinity to infinity, all real numbers. That's exactly the opposite of what we saw with exponential functions. So the domain of a logarithmic function is the range of an exponential function, and the range of a logarithmic function is the domain of an exponential function. So the x-intercept of a logarithmic function is 1, 0. It has no y-intercept. Contrast that with an exponential function, which has a y-intercept of 0, 1, but no x-intercept. For a logarithmic function, the y-axis is a vertical asymptote. We saw for exponential functions, the x-axis was a horizontal asymptote. For a logarithmic function, if the base a is greater than 1, the function is increasing. If the base is less than 1, then the function is decreasing. That actually is identical to what we saw with exponential functions. The same properties apply for exponential functions. And finally, logarithmic functions are one-to-one. Every x is associated with a different y value, so it has an inverse. That's also the same as exponential functions. They are one-to-one, and they have an inverse. Now I'll discuss this further in the next video, but what we're basically saying in talking about these, in comparing the properties of logarithmic and exponential functions, is that logarithmic functions and exponential functions are inverses of each other. So in the next video, we'll explore that relationship further.